Good morning, good evening, everyone. Welcome to this webinar, Artificial Intelligence for Space. I'm Ivan Sumelzo, and on behalf of SGAC, the Space Generation Advisory Council, I will be hosting this webinar today. This webinar will be organized as follows. First, we will have 5 minutes of introduction for presenting the topic and the guest speakers that we have with us today. Then we will have 3 presentations in total. Each speaker will have 15 minutes of presentation to talk about artificial intelligence for space. You will see that what's interesting today is that each speaker will attack the topic from a different angle. And finally, we will have a Q&A session of 10 or 15 minutes. So I invite you to use the chat below to address your questions, and we will try to address them at the end. So why this webinar? Why artificial intelligence for space? Well, we are living exciting times these days, since more and more space applications are starting to benefit from AI algorithms. There are many examples: satellite image recognition, space traffic management, spacecraft operations, either on ground to facilitate operators' tasks or on board to improve spacecraft autonomy, AI for assisting astronauts, optimal management of scientific or telecommunication payloads. I don't know if it's a coincidence, but this weekend, the European Space Agency is going to launch the very first European satellite to demonstrate how onboard artificial intelligence can improve the efficiency of sending Earth observation data back to Earth. It is called the FEE satellite. So everyone agrees on the interest of using AI for space. The problem is that sometimes we see AI as magic, as something that is able to solve all the problems of the humankind. But this, of course, depends on many factors. What type of problem we are solving, what kind of algorithms we are using, what time and how much data we have available. So in order to better understand all these concepts, a good idea is to discuss with experts that actually have real experience implementing AI solutions for space applications. It will be too difficult to cover today all the potential applications in just 1 hour, but at least thanks to them, we will have some real examples to understand what kind of things are already possible today and also to imagine all the possibilities that we will have still ahead of us in the coming future. So let me present you the guest speakers. First speaker will be Juan Peña, Ibáñez. He is a space tech entrepreneur and CEO of Orbital EOS, a Spanish company developing solutions based on satellite data and artificial intelligence. He's currently involved in R&D projects of cubesat missions and high altitude pseudo-satellites with the scope of addressing environmental challenges in the maritime domain. Something interesting, the European Space Agency has selected less than 1 month ago, Orbital EOS as one of the 10 finalists of the ESA startup competition. So Juan, congratulations for this recent achievement and welcome to this webinar.
So thanks a lot, Ivan, for your kind presentation.
Second speaker, Rashid Avai, founder of Futurify. He's artificial intelligence and machine learning algorithms engineer for space applications at University of New South Wales at Canberra. He's currently pursuing a PhD in aerospace engineering with a specialization in astrodynamics and machine learning. Rashid, we have been sometimes doing the same astrodynamics competitions as rivals. Well, I think you perform better than me, at least in the last one related to space debris and machine learning. It's a pleasure to finally meet you today and welcome to this webinar.
Thanks, Ivan. I'm really happy to be part of this webinar, and I also welcome all the audience. Thanks.
Thank you. I hope it's not too late right now in Australia for you. That's the advantage of doing a webinar, that we can connect with people all around the world. And last but not least, the third speaker will be Dr. Redwan Bomgar. He worked on many different artificial intelligence projects in robotics and perception in the satellite imagery industry. He's a former research fellow in the team for AI in spacecraft operations at the European Space Agency. Red believes in open interplanetary collaboration where space is claimed the liberal way. That's why, as core contributor to the Liberal Space Foundation, he shares and maintains a fully open source machine learning project for future autonomous space operation. So Red, I know this is not your first webinar these days. Thank you very much. I hope you are not too busy with all your projects in parallel. Welcome to this webinar as well.
Yeah, thank you very much. I'm super happy to be here.
And just some last comments before starting. As you may know, due to current COVID-19 situation around the world, SGAC is proposing many interesting webinars during these days in order to keep the community active. I invite you to check the SGAC website to have a look on all the events that are being proposed. This event today precisely is part of the European Space Generation Workshop. This was an event that was going to happen in Madrid in the beginning of May, but it had to be postponed to the last weekend of October. The idea is to organize a panel on AI for space, but in the meantime, we have decided to organize this exciting webinar virtually. So I would not like to take more time. Enjoy. Welcome to this webinar, and let's start with the first speaker, Juan.
Okay, I think you properly see my screen, right?
Perfect, Juan.
So, good morning, everyone. It is a real pleasure to be here with you this Sunday morning. Thanks to the SGAC for inviting me to this webinar. My name is Juan Peña. I am the CEO of Orbital EOS. We are a Spanish company developing solutions based on Earth observation and artificial intelligence. So the title of my presentation is Earth Observation for Ocean Resilience. I will be presenting some job we are doing with satellite imagery in order to address marine pollution at sea. So I wanted to start this presentation with these two smiley faces of this gentleman. I think we are all aware of this recent achievement. These two American astronauts made it to the International Space Station with the first commercial rocket mission to the ISS, which is a huge step in the space community. And I think it's just the first step for the things that we're about to see this decade in advancing in space exploration. So, as I said, today is Saturday morning, so I thank you all for being here rather than being with friends outside. I don't want this to be a boring presentation, so according to the people who know about these things, you have to tell a story about what you do, and that's exactly what I'm going to do. I will tell the story of my company, how we started. So it all started here at 4,000 feet over the Mediterranean Sea. The founders of the company, we had the opportunity to work for the Spanish Coast Guard for more than 10 years on board this flying laboratory, and we had two main roles: search and rescue operations and also marine pollution monitoring using airborne remote sensing. So here you can see a summary of the activities that we had the luck to do those years. So we had to control maritime traffic, detect and characterize pollution, search and rescue operations. So it was quite a very interesting and dynamic job. This is a picture of the aircraft from the inside. Basically, we used integration of sensors that gave us real-time data about what was happening at the sea. And for the ones who are not familiar with oil pollution at sea, I would explain that the main sources of oil pollution are leaks from offshore facilities, also illegal discharges of oil coming from ships, and accidents. Although accidents are the most famous source of oil pollution at sea, they only count for around 10% of oil pollution that is ending up at sea. So this is an accident we had the opportunity to work on, a very large fishing ship that sank in the Canary Islands, and we had a small crisis. So we had to cover this crisis using airborne remote sensing to characterize the pollution. So the challenge here, as you may guess, in geographical terms is big. We currently have around 95,000 ships in the world and around 1,400 oil rigs. The area of the oceans covers around 2.5 times the area of continents, so it's a huge task in monitoring. And according to United Nations Environmental Program, approximately 2 million tons of oil end up at the sea each year. And more importantly, most of that goes totally undetected. So we started to wonder, we started to reflect about this thing. If we can better understand marine oil pollution on a global scale, and how could we use Earth observation satellites to better address this task? So in terms of data collecting and data processing, you can understand that the challenge is amazing. Where we are addressing here to collect a large amount of data from satellites, basically covering the whole planet on a daily basis, and also processing and analyzing all this data so we can get accurate and agile outcomes. So let's say that we did all we could all these years. We joined a master program in remote sensing and data analytics at the University of Valencia. We visited the European Space Agency 3 times. We joined every webinar and event that we could join in, and we also did our own research about spectral signature of different kind of oils. So in a sense, we embraced the ambitious and naive attitude of entrepreneurs. Yes, we can. And in the present is actually what we do. So we now fly higher. We use constellations of satellites to detect and characterize oil pollution at sea on a global scale. We use radar satellites and optical satellites as well, as currently 2 different constellations of satellites that use sensors that could be used to monitor oil pollution at sea. These would be some examples showing how we can use these satellites to detect, for instance, an illegal discharge of oil. This is an example here in Spain, the Strait of Gibraltar. In this case, we will be characterizing the event with a synthetic aperture radar. This is actually Sentinel-1. Another example, very, very clear. And this is a very big spill in which you can see the reference of the ship. The ship is actually 200 meters long, so you can understand the size of this event. So the next thing we are doing is a challenge that has not been solved yet, and is the automatic detection of oil spills in satellite imagery. So we have, as I explained, we have embraced the AI for Earth observation community, which is very, very active, actually. For the people who work in this field, we are in the intersection of several disciplines like image processing, signal processing, machine learning, and computer vision, which is very, very exciting because the interaction has many, many synergies. And in order to address these issues, the field that we are using is classification, or in a more broad sense, pattern recognition. So what we are trying to do in generic sense is to imitate the way our human brain works, right? According to Edward de Bono, who is a very famous psychologist and father of the concept of parallel thinking and leading figure in creativity, he described that the brain works creating patterns and patterns. So in that sense, we're trying to imitate how our brain works. Our brain works taking information as an input, learning about this input, and providing an output. So as you may see, the input, the information that we use to train the algorithms, to train the artificial intelligence, is very, very important. The quantity and the quality of the information that we use to train the algorithm. There is an amazing job done by the group of Sebastian Thrun, who is a leading expert in artificial intelligence right now. They published in Nature a recent job about detection of skin cancer using pictures. So this is the field of artificial intelligence that we call expert-driven AI, because we need experts to tag images. This wouldn't be a case in which we try to detect cars or ships. Everyone knows how to recognize a car, but not everyone can recognize skin cancer, right? So we need experts in order to provide this quality information. So I encourage you to read the paper. It's really amazing what these guys achieved. So this is what we're doing is very similar. This would be a satellite image with some oil spills in the image. It's quite tricky to understand where the oil spills are. So you need a lot of training and crucially a lot of experience. I'm showing here the outcome. So this would be showing where the oil spills are. So we are generating a huge database of cases in which oil spills have been detected. Also other cases in which that there's nothing to report, or natural features that are not currently oil spills. And that's where we are involved currently. So my vision about the future in the use of AI for Earth observation would be something like this. The future will be very smart. We will use, as Ivan was explaining, smart satellites that will take decisions in orbit rather than sending only images. So they will, in a sense, help us in providing real-time data, because the data would be so large, the downlink wouldn't be so much problematic as it is currently. And also for me, the satellite intelligence based on Earth observation will be also accessible to anyone. I think it will become a commodity. So this is, in a sense, it is very, very good. So everyone can, for instance, get information about what is happening in the planet from their own iPhone, asking questions to constellations of satellites to understand in real time what is happening in the other part of the world. So these amazing things, from my point of view, will happen if we all behave in a responsible and ethic way. And of course, we take care of our home. So thanks a lot for your attention. I'll be happy to answer your questions later on, if I know the answers. Thanks a lot.
Wow, Juan, thank you very much for your presentation. I'm sure the audience will have questions. I invite you to use the chat below, and we will try to address them at the end. So now I propose you, let's pass to the next speaker, Rashid Abai.
So can you see my screen, Ivan?
Yeah, I confirm you. We can see your screen.
Yep. Hello, everyone. I'm really glad to be part of this webinar, and I'd like to thank all the organizers for the invitation. My talk for this webinar will be on the applications of AI and machine learning in space domain awareness. I am Rashid. I'm the founder of Futurify, AI machine learning engineer and astrophysicist. The outline of my webinar, I'll start with an introduction of myself. Then we will move to the next question. What is space situational awareness and domain awareness? What is the difference between them? Then the next one, why do we need AI and machine learning in this domain? Then I'd like to just walk you through a competition that I had the experience applying AI and machine learning for real problem in SSA, which was related to collision avoidance. And at the end, hopefully, I'll be glad to answer your questions. Let me just talk about my journey ahead. I started my career as a computer engineer, and my thesis was related to AI and image processing. But these times, like before 2012, not that popular. AI was just something that you can try. And, you know, even using 3 layers was, oh, what are you doing? All those times. And then I did my master's in space systems engineering. And my thesis was related to a new orbit prediction algorithm based on Kolmogorov-Arnold-Mozart theory. Currently, I am a few months away from submitting my PhD, which is related to AI and machine learning applications to characterize high area to mass ratio objects. In SSA, such objects are extremely important because they have very complex attitude and orbit evolution. So we need to understand how they behave to make sure they are debris. And all this experience, multidisciplinary ones, led to my business, Futurify. With Futurify, I provide solutions to various industries, AI and machine learning solutions, ranging from horticulture, agriculture, vessel tracking, and of course, naturally, because I am astrodynamicist, space situation awareness, and space in general. Okay, let's get technical a little bit. What is space situation awareness and what is space domain awareness, which is a term borrowed from air domain awareness and also maritime domain awareness. Space situation awareness concerns with the elements, space objects, the volume of those objects and their temporal behavior in time. So this is like a more physical. And if we add SSA to SSA, the decision-making mechanism, ground segments, operators, now we are talking about space domain awareness. So if anyone else who confuses these, this is my very simple explanation what the difference is. And from now on, I'll use SDA, but sometimes I'll talk about SSA indeed. Okay, let's get deep in the details. So what do we do when we do space domain awareness? So space domain awareness starts with collecting raw observations. And the modality of data can be image, can be RF signals, or something else. And then once we have those observations, we do inverse mapping. From the signals, we try to get the attributes related to the object that we are observing, which is called characterization and identification. And next step is determining the objectives and intent of the object that we are observing. It can be weather satellite, it can be surveillance satellite, it can be just debris, a high area to mass ratio. And finally, once we just follow all this pipeline, we can predict whether or not that object that we are observing is a hazard to any asset that we have. If you look at this whole pipeline, you will realize This is typical data science pipeline. You start with data, end to end. You, at the end, have the decision, threat or not, just like a classification. Okay, what is the challenge? What are the challenges in this domain, space domain awareness? Because like when I think about AI and machine learning, I always ask the question, can I use machine learning and AI to solve the problem? Because basically it's just a solution to some problem. It's a tool. Let's just investigate the challenges first and move how we can just address them with AI and machine learning. In classical sense, when we try to get the attributes from observations, we use simple parameters related to physical properties. We call all objects like, you know, they are cannonballs. They have same reflectivity. They have, you know, same properties. And we give them just an estimated parameter. But this is not enough, because 1U CubeSat is very different from Hubble Space Telescope. Of course, with the cannonball, you can define the size, but what about the shape, material property, everything else that interacts with the space environment that leads to the deviation from the known dynamics? As you know, known dynamics are gravitational dynamics. If the properties, physical properties are extremely complex, then the interaction between the space weather or in the space environment and the object leads to the divergence. So it decreases our knowledge when we project the behavior into the future. So this is the one of the challenges that we need to address. The second one is related to the amount of data that we need to address. We are launching more satellites. We are coming up with new sensors that leads to new observations. As you can see, there is this trend increasing objects, and maybe in a couple of years, we will have hundreds of thousands of objects that we need to catalog because we can observe them, and also we are launching more of them. So if we have human in the loop, it is extremely hard to tackle such time-consuming tasks. So we need something that can do what we can do. Before maybe going forward, although I didn't want this to be like, oh, okay, this is AI, this is machine learning, for audience who might not have that experience, let me just talk a little bit about the what the AI and machine learning in essence. To me, it's just differentiable programming. When we build an AI algorithm or machine learning algorithm, end to end, we search for useful representations. So basically, it's just trying to learn a coordinate frame that decides the decision boundary between different classes. So how we do this, we need to have the elements. We need to have the data. We need to have the optimization scheme. We need to have the objective function. We need to have the gradients that will walk us to the optimized parameters. And finally, we will have these parameters that will give us the mapping between input and output. The way that I explain this is for supervised learning. But another signal can help us. We don't have to just give, oh, this is the target that you need to get. Maybe this can be due to the interaction between environment and the agent. And now the signal can be just reward. So this is basically, in general, what AI and machine learning and how we build those algorithms. Let's move to the question, why AI and machine learning for SSA and SDA? Because we covered SDA, what it is, how it's different from SSA. And we a little bit just touched AI and machine learning in essence. So why would I use AI and machine learning? So first, AI and machine learning is very helpful when we try to discover from data. Although we don't know anything about the model or the behavior, by just having the data and building our end-to-end pipeline, we can learn from the data itself. And the second advantage is related to the capability that it can handle large amount of data. And interestingly, having more data is better for AI and machine learning algorithms. I'm talking about high quality data, but still having more is always better most of the time if they are good quality. And at the end, finally, those algorithms can learn from data. So that can help us to automate the procedures and tasks, which will make the tasks and operations less complex and easier to handle for us. Let me give you a couple of applications that I experienced for research and also in industry that is related to space domain awareness. One of the challenges that I had was related to estimating mean orbital elements from time series oscillating elements. Let me just explain what I'm talking right now. Oscillating ones kisses the real orbit at one time only. Then it just deviates. Let's say we have such real points that just touches the reality, and we have time series of them. We need to be able to map this time series orbit information to just some vector that explains, that just allows us to fit the whole real trajectory. So when we estimate those parameters, we always need to do some type of optimization, but we don't know where to start. Each time we need to just search for the best place to start to do the local optimization. That's why I had this experience with SGP4 and TLE for space operations. And indeed, it's the only time that I feel wanted as an astrodynamicist. When someone else launches something, they need to communicate with it. That's why I estimate a lot of TLEs. And then I had this idea, oh, why I'm doing this again and again? Let's just learn from the experience. Then I investigated this phenomena, and I realized that it's possible to learn where to start when we are estimating these. Second example, the second experience that I had was related to collision risk prediction from historical collision data messages, which I'll talk in detail momentarily. So I'm just stopping at this point. The other one is related to light curve inversion using machine learning. As I mentioned before, when we do the observation, we have some type of signal that we need to get the attribute of the space object. Is it rotating that high velocity, angular velocity, or is it just made of this material? So all these needs to be mapped from this signal only. So I use machine learning, most of the convolution networks to do this mapping, and then I realized still AI and machine learning can handle such inverse mapping problems. And naturally, the other example, other experience that I had was related to processing of optical telescope images. Once you have those observations, you have streaks of the stars and also the area of interest. Because of the variation and the exposure of everything else related to the telescope, it's very hard to come up with rule-based mechanism that can tell you where the area of interest are. And I use some segmentation algorithms based on UNet to solve this problem, which is pretty efficient. And finally, currently, this is something that I'm working on, which is kind of Internet of Things and Edge AI application, distributed autonomous space surveillance. So let's say we have, telescopes dispersed all over the world. Are we supposed to put someone else who needs to take care of all these observations and the analysis? Anyone else who conducts such operations will know it's extremely hard for a human to do all these tasks. So this research that I'm working right now will try to automate this process in a non-centralized distributed fashion. Let me just talk about one of my experiences that might help audience to know when to use AI, how to use AI for real SSA problem. This challenge was publicly available by ESA, and also I know Ivan also just participated in this one as well. So the whole challenge was about predicting the risk before 2 days. Why this is important? Because active collision avoidance is the only way that you can avoid probable collisions. However, starting from 7 days to the close approach, you always receive collision data messages. However, not all of them are meaningful. Some of them are just warning that will never pan out the real warning or real close approach. So then the ESA had this idea, okay, can we leverage AI and machine learning to predict 2 days ahead if this close approach is a risky one? And then I just said, oh, okay, this is for me. And I started investigating the dataset itself to understand or to have a feeling of how I can approach this problem. The first thing that I realized is the dataset itself is quite small to attack this challenge. And I tried to do a lot of domain-driven approaches to solve the problem, which just gave me some edge at the very early stages. But then I asked myself, okay, if we want to deploy this for real life, we need to be able to come up with a scalable method that can let us know what will happen in future. So that's why I continue my quest to be able to solve this problem using AI. And then what I realized after doing some feature engineering, there is this distribution difference between normal and abnormal cases. Normal cases are when the collision risk for up to the second day is smaller than 10 to minus 6, then it leads to 10 to minus 6. But the abnormal cases are, it looks like 10 to minus 6, but then at the end, it just becomes very smaller than this value for the close approach. Then I had this idea, okay, this data is small, so it's hard to learn. Then maybe I need to learn what is the difference between normal and abnormal. And I just did a lot of investigation, and then I came up with this paper related to Manhattan LSTM. So basically, this architecture compares normal and abnormal cases and let us know which ones are similar, which ones are not. And I built a lot of ensemble of models that will reduce the overfitting, and also I decrease the features that I can make use of. At the end, this gave me 3rd place in the competition by using AI, and I was only one who applied AI in the top 3. This is the end of my presentation. Hope you enjoyed it. I'll be waiting for your questions at the end.
Rashid, thank you very much. We have passed from taking care of the oceans with Juan using AI to taking care of the space environment and all the objects that are orbiting around the Earth, and how to use AI to manage all that, thanks to Rashid. So I hope you are enjoying so far the webinar. Again, make use of the chat in case you have questions, and we will address them at the end. Now, let's give the screen to our last speaker today.
Hello. This is Red.
Hi, Red. I think now you have the right, so the screen is all yours.
I have it, yeah. I can share my entire screen, so it's... Hello, everyone. Can you see me? Yes?
Yeah, you are in the middle of your presentation.
I'm in the... Exactly. So I thought that I would present myself also like this. I like to see the faces maybe at the end. I hope we can make a group picture. This would be nice. So yeah, short about me. I think Ivan said everything in the beginning. I don't have a straight path in studies. I did fundamental physics and then satellite imagery, AI, and robotics as my PhD. And today I'm going to present some views on AI in spacecraft operations, and also share with you how it discovers space operations, because this is the backstage of space. Nothing happens without operations, and I think sometimes we kind of misunderstand what's really happening over there. So everything that I speak about here are my own views, because you can check out my last employers on my LinkedIn, so I have to say that. All right, so let's get started. So I'm a co-contributor of the Libre Space Foundation, which means that I need to present what this is. So this is a foundation to enable open and accessible outer space for all. And I think with the council, this is a great opportunity for me to speak here. It started with actually enabling the access to spacecraft telemetry with ground stations, like you see on the 3 photos on the left. They are in the end, let me just get rid of something. What is that? Okay. So in the end, they are ground stations you can build yourself, because they are open source. So so all those ground stations you can build yourself from your garden, and those are pictures of real people antennas. And the foundation is providing this knowledge from the ground to space. So also on the other side, you have a CubeSat here, which is fully open source, which you can build yourself as well with, with the support of a university or a larger lab. You need some kind of facilities. So the goal is to claim space the Libre way, to open source everything, all the knowledge, and to enable everyone in the world to access that. All right, so there are things happening in the last years which we call the new space, that you hear that especially at ESA, but all around, as they and that impacted also the evolution of operations. So operation starts when the satellites actually detach from the launcher. Okay, so this is when the satellites has to communicate with Earth by itself, and therefore operation starts. And at the launch, you have on the left you have the launch site, and on the right you have actually former colleagues. I was working over there, not in this room, but what you can see is that you have two rows in the front, which are mostly spacecraft operation engineers taking care of different subsystems. So for one spacecraft, it's quite a big team. So and you will see that this can't be like that for the future missions. So here you have this governmental, intergovernmental missions. This is Sentinel-1. This is a radar satellite, and on the right you see the team operating this satellite. That's quite a lot of people. Hopefully they operate another satellite at the same time, of the same kind or the same mission, and they are versatile. They can do several satellites, because most of the time everything is in good shape of operation. So there's no need to worry too much. So mostly the people are really busy at the launch time and the commissioning phase, meaning just after the launch, trying to take care that everything works perfectly and that the satellite is going to produce the data that we need on Earth to do our analysis. But things are changing. So as you see here, this is the Starlink mission from SpaceX, and this is an example, but this is not the only company going into this. So you have like the launch of about 60 satellites. So here, this is an astrophotography from an amateur taking this just after the launch, and all the satellites are quite grouped all together, but they're going to reach their orbit and split and have this kind of constellation setup. And so far, this is a challenge for operations. So, how do you know which satellites you're communicating to, and how do you send the commands correctly? How do you check them out, and those kind of things. So, and also with the small satellites like the CubeSat, which is a 10 by 10 by 10 centimeter satellites, usually you use 2 units. So you have longer satellites where you can put more things, a bigger camera. You also have like pocket cubes. Smaller satellites have the side of such a cube, so a quarter of the volume, and we need what's what's the goal for operations? That's the telemetry. So we need the telemetry to operate those satellites to check their health for doing health monitoring. And so the SatNOGS mission is actually providing that from the Libre Space Foundation. You have an open data set of 400 satellites. At least 40 of them are well documented and usable, and that's a good thing for us. But the operations are not just like putting things in orbit. It can be more complex. You have engineers take extra care, and so they make their mission live longer. But here you see the diagram for Rosetta. It took 10 years to reach a comet, and on the way it actually woke up to take pictures of different flybys for different bodies in space. And on the right you see actually the path that the satellite was taking around the comet while moving with the comet, which was also a challenge because the gravity around the comet was not continuous or regular, isotropic. And you have different challenges in operations also, where you have like human machines interactions. Here, this is the Maritime project. The scenario is you have an astronaut going to a far body and sending a robot on the ground and commanding it. This is not really autonomy, but that's where it can go as a scenario. And for more autonomous things, you have those robots which are not fully autonomous. Apart from curiosity, I think on the last periods of its mission, they took the opportunity to try to have it more autonomous. But we're going to see that more and more. So exploration of our solar system is going to be probed with a lot of all those mechanical fellows. And this is coming, and we need more autonomy. So Europa Clipper is going to a Jupiter moon, which is very far. It's like 30 minutes to 50 minutes of one-way light time. This means that you need to wait 50 minutes for your message to arrive there, then 50 minutes for it to come back on the worst case scenario on when you're far in the orbit setup. But also we're going to see like fully autonomous space drones to do exploration of the solar system in a more systematic way. For mining, there's a lot of startups listed and actually studying that. And what the future holds, we don't know. It's building and eventually fighting when we see what in 2018 the US is doing with the Space Force, catching up with the US and China. Space has become a military domain as the sea and the ground and then the air. So and the cyber area. So let's take care of that. That will make everything peacefully. And then you have the assistants. So for operations, they assist. The goal is to assist astronauts, to monitor what's happening in the station at this moment, because not everything is connected. You have to check out numbers on the screen or something like that. So this could be a useful fellow also to tell you what's the status of the station and trying to understand what's happening with the station. So we're moving towards more AI as a key member of your operations, and you can see a small evolution like on the top left. This is Eutelsat in 2015. You still have 70 people for 27 satellites. This is much better than a scientific mission, but still you have one screen, one satellite. This is quite a lot. But then on the right you see like screens with multi-purposes and engineers of multi-purposes. And what I hope we'll come to is actually this Jarvis. I mean, this would be great, and the assistant that knows it all and actually plans things for you and actually proposes you different alternatives. So I think reinforcement learning is involved and all this kind of great tools. And for the Libre Space Foundation, we are leading the machine learning project called Polaris. We are building machine learning tools for autonomous spacecraft operations, and at the moment we're focused on reducing the operator workload. So we use data, as I said, from the SatNOGS stations. You can download the blueprints, build your own. At the moment we have like about 219 up and running, but it's about more than 1,000 in the pipe. I could turn up. And this means that all over the globe we have some kind of a coverage. I mean, we still have to get some fellows in China or in the South Hemisphere. Maybe I'll talk to you, Razit, for Australia. So therefore we get data. So, and the last one we covered is Quetzal-1. This is the first Guatemala mission, and this is a CubeSat. So, and you can get the data and see what's up on the CubeSat. So, some battery temperatures looks okay, but the heater is on, so it's consuming energy, etc. And as Razit was saying, there's more data in the context than just telemetry, and we need to take that into account. To understand when an anomaly occurs, we need to understand what's the source of the problem. And machine learning algorithms are pretty good at actually see what's important in predicting an anomaly. So that's what we do. We're trying to gain knowledge from a spacecraft, and we do that with different machine learning algorithms. The main one is random forest based. In XGBoost, we're using XGBoost on this one. We're extracting the importance of all the features, I mean all the telemetry on one that we want to predict. And then each node on the graph is a telemetry, and each link has been reported as a link to an important telemetry to predict that one. So it's a directional graph where your nodes are telemetry, links are dependencies, and when you zoom in, you have particles that actually shows with their speed, the faster they are, the more impact there is between those two nodes, and the color are semantics. So in red you have a subsystem, in green another one, etc. So this led us to thinking, we're using a graph. That's actually a study I was doing at the European Space Operations Center, using a graph and showing that to the Mars Express operators. I realized that they actually, the first time, they're discovering, they mouse over, they see the name of the telemetries, they see different things. And it's important to have this interaction between, and this understanding between the output of the machine learning or the AI algorithm and the human being. Sometimes it's so multidimensional that just a sentence doesn't suffice. And so here you see bubbles, the reaction wheels, the big blob in yellow, that's the power system. They code that on the first test. Then the next week I showed them the same graph. It's a dynamic graph, so you can move things around. And it was rotated, but they saw that that's my spacecraft. Okay, that's Mars Express. And I know if I see the graph of XMM Newton, the X-ray Observatory of Europe, I would recognize it as well. So the eye is an amazing piece of catching patterns, and we have to use that. So what's important is the layout algorithm. I'll just pass quickly on that. That you got it. But in the graphs that I showed you, it's just links between telemetry and their dependencies. We want to go further by studying the behavior of each telemetry and linking the behavior changes instead. And this is a computational graph from a startup company called Arabesque. And what you have here is the link between data, and the links are computations. And it's trying to find the best path to actually make the best output according to your own problem. And maybe we're going through that because we start to have pipelines, but the next step after pipelines, I think, and I believe, this is the computational graph. So I told you that the understanding what the algorithm is saying is important. So when we have onboard AI on spacecraft, we need to explain how the decisions were made. Because as soon as you have an anomaly, you need to audit. You need to see what happened in the past. Quickly tell me like what happened in the last orbit. And here I give you an example of a neural network which is actually pretty well behaving, making the difference between a wolf and a husky. The thing is that it shows you the picture that it has as input to get those labels correctly. There's only one mistake over there. You see over there, it predicted a wolf instead of a husky, and then in the picture on the right of each couple of pictures, you see what made the decision, the region of the pictures that took the decision, drove the decision of the algorithm, and you see that sometimes has nothing to do with the wolf or the husky. Huskies are taken into pictures in different places. The wolf always in the snow, so the snow is kind of high importance. So it's important to know what made sense, for the algorithm. So we're here with the Polaris project. We have this graph. We are trying to explain to people that they can actually backtrack problems. They go on a node and they can see the shortest path to another node that they think is giving the problem. Have a problem on the battery, but this is linked to a current on my heating subsystem, and you can make the link like that. So this will conclude my presentation. I hope I was not too long. We love to interact and we love contributions. We're all doing that on our spare time on the Polaris project, and you can find us on the web. So we're trying to build things together, and I think building things together is one of the only good way to build things ethically. So you can find us on GitLab for the project, but on Matrix, where the URL is here, using the Riot application. This is just like a discussion channel. It's a live channel, and you can join and see us there and ask your questions and even share your ideas. I haven't seen the question pad, but I'm sure I hope I raised some ideas. And we sometimes have video conferencing. And the team at the moment is spread between Canada and India, so it doesn't matter where you are. We'll try to accommodate. I mean, even Razit is in Australia. That's starting to be a problem to find a good time spot for meeting. So that's it. So I told you a bit that we're trying to look for behavior analysis, which is on the other side in purple. And but we need more interaction with spacecraft operators. We need to show them the graph to understand what they really need, in 2 days missions, and also because the circles in white over there in blue, we need the operation plans. That's one missing piece of the information of the satellite mission. So with this, that's about it. So I hope I was clear enough. And oh yeah, behind me there was like some ideas. We want to do continual AI because we're getting data day by day, not as a bunch. So this is kind of a different way of thinking about machine learning. And eventually doing reference smart learning on the operation plans, changing it and seeing what's happening, different scenarios. What if? Okay, thank you.
Thank you very much, Red. Amazing presentation. I will invite you, Juan, Razit, and Red, if you want to turn on your camera, so it will be easier to answer the questions, and maybe one question can be answered by more than one speaker, of course. Okay, and then Red, maybe he has the ability to appear somewhere else in the screen. Okay.
Yeah, I'm actually in flight to Jupiter, but
awesome.
That's why we have problems with the time zone. I never know when I'm on which time zone I am.
So since we have started a little bit later, I propose you around 10 minutes to answer the people's questions.
All right.
We have a first question from Sereya. I think it's for Juan. She asked, how can AI help in analyzing Earth observation data to evaluate the economic activities during the COVID-19 outbreak?
Okay, that is a very, very nice question, actually. What can be done, for instance, is to understand movements of people, counting cars, for instance. If you can count cars in the parking lot of an hospital, then the number of cars that you can count on an hospital tells you something, tells you about if people is going massively to the hospital, if people is not going. Or you can do that also in the industry. If the people is going to work, or if they're not going to work, if they are violating, let's say, the lockdown, for instance. So one approach would be to count things that we use to move like a car. Of course, we need cloud-free imagery, and we need a place where cars can be seen from the satellite. It's not on the ground. That has been proven already for instance, monitoring industrial activity in other countries like China.
Thank you. Juan, for your opinion and your answer. Then next question, I think it's a difficult one, but also it's really interesting. It's related to astrodynamics and maybe spacecraft operations. So be ready, Rosita and Red. They ask if you know about the application of manifold learnings in interplanetary maneuvers design. So I'm thinking about going to the Lagrange points and things like this. We can use machine learning algorithms on those scenarios.
Yeah, thanks for the question, Ellen. Indeed, it's something that I tried to do. Yeah, for third-body systems, which we investigate learning the manifold that we can learn. The manifold is not the manifold that you mentioned, like the manifold empirical distribution of what is the dynamics between planetary motion. But then what I realized is the accuracy, the precision, that is the problem. Because the distances are extremely large, and the GPUs are not good, they are not double digits, right? They are not just, sometimes it's just like the single digit. And then how can you learn, let's say, 10 fractional points? I'm not talking about the manifold learning that you mentioned. Even just trying to learn something that precise is very challenging for machine learning. Machine learning is more like, this is the surrogate solution of my problem. Let's say, if you look at the ImageNet problem, it's just 1,000 classes. It's just 1,000 classes. So it is used to compress higher dimension to lower dimension. So I think we need to just change our thinking when we try to use AI and machine learning in that sense. It's not for precise numbers. It is for the decisions. I think it helps for Ellen.
Red, maybe you want to add something. If not, I have a question for you that is arriving soon.
No, I think that's Rosita answered greatly. Nothing to add.
Okay, we have a question about AI explainability. How do you verify that AI-based systems do what they are supposed to do, and how do you validate their decisions? I guess that sometimes we are afraid that AI is like a black box.
True.
We don't know what will happen.
True.
How to ensure that?
That's a very good question, Marin. Actually, this is a critical one for acceptance of those systems. Actually, behind me, there is no pilot because this is AI driving. And but it took some time for me to be confident that I should not look. The thing is, that's really about confidence. So how things are validated today, they're validating thanks to history. So that's they made their proof. And today we have this problem that if something has never flown, it will never fly. And there is one good mission from ESA called OPSAT, so Operation Satellite, which is a 3-unit CubeSat on which you have redundant computers, so you can change everything, even the onboard system. So you can fly your software and test it in flight. So you can say, okay, now it has flown, so it can fly on another satellite. So that's one way to have new things in space operations. But when we talk about AI, where it's eventually undeterministic things happening, you need two things. You need, of course, the auditing and the monitoring of what's really happening. So you have a lot of explainability tools that does that perfectly and explains ensembles, but also neural networks very well. The one you've seen is a convolutional neural network on a husky and the wolf, and I kind of give this explanation on what was important for the decisions, and that's what you really need to know. But then when you use that in a system, you need to use it in parallel with the traditional system, so that you kind of build your confidence that, okay, the decision taken by the AI was the right one. I chose it, and bit by bit you say, okay, I just go with the decision, and then we'll see.
Thank you, Red, for the answer. Next questions is we have two questions for Juan, I guess. First one is, how can we safeguard access to real-time satellite data among the public? I guess that AI algorithms perform better the more data we have, but maybe we don't have access to all the data that we would like. What's your opinion on that?
Well, in my opinion, that is related with ground stations and the way, as you know, these facilities are very, very expensive. So the more investment we have in ground stations, the more available data will be. But at the same time, I see that in this decade, we need to go beyond that, and we need to understand to provide better ways and cheaper ways to downlink data in a very agile way. As I explained, one thing would be, for instance, that the satellite is sending us data which are kilobytes of data, not gigabytes of data. That would be one approach for me. And the other way would be to have satellites in the middle as another layer from the satellite, which is orbiting at 700 kilometers above the Earth. We would have another constellation that is in the middle. So it's helping the global reach of this downlink capacity. That would be my opinion.
And second question was, can we classify the oil spills based on the severity using satellite imagery and AI?
Well, the question, okay, the answer would be yes. Basically, severity is related to quantity of oil released at sea. So in that sense, we are working hard with optical data sets. This is a new field in oil spill science. So we can, for instance, quantify the oil. The impacts, the environmental impact is highly related with the quantity of oil released at sea. So the answer would be yes, it can be done.
Okay, thank you. I think it's another question for Red, or maybe.
Yeah, I've seen it. Yeah, the open data set.
Yeah.
I think Bernard, that's a great point. In my conclusion, I actually said we need to talk with operators because that's the information they can give. You know, there was an anomaly here, and we spotted it. So we already have the housekeeping telemetry, which is open source thanks to the SatNogs project in naval space, but we don't have the anomaly reports. We have some of them, you know, when the operation team is close to the project, they even have their own ground station in the network. We do have that, but that's something we should be building in the future. But also with the Polaris project, what we're trying to do is trying to have this unsupervised approach with the only assumption that most of the time everything is fine. You know, that's why you get so many beautiful pictures from space. It's because the spacecraft actually work. So we don't have many anomalies. That's the issue.
And thinking about the future, next question is, how close are we in implementing reinforcement learning for control systems and robotics in space? We feel that it's something that is going to arrive, but when?
In space, I don't know, Razit, if you have an idea on that, but it's of course, you know, on ground it's already there. The thing is that if you think about reinforcement learning for control, you know, the best approaches I've heard like last month is, you know, 7 million iterations, something like that. It's a bit crazy. So you can't take the time to do that in space. So maybe there's like some kind of an hybrid approach where you do things on the ground with a high computing power, and then you upload the last models.
So for a question for Razit, in terms of space traffic management and the computation of collision maneuver avoidance, how do you imagine the future? It will be the satellite on board that will take the decisions, or it will be always a ground algorithm that has a global idea of what's happening around all the orbits or the catalogs and will send TCs in order to conduct those maneuvers or not?
I think, thanks for this, Ivan. I think it's related to the question itself as well. Like, you know, learning how to control in space. Then I'll ask the question, do we have any representative data to solve the problem? So then what the agent will learn will be based on what you feed into the system. Let's say this is a reinforcement learning problem, and then you try to learn how to control the vehicle itself. If the data itself is not representative, then the end result is nothing. It's just, you can't use it for real life. And this is the biggest problem when we apply machine learning and AI in real world problems. If you don't do the right thing, at the end, it's just, garbage in, garbage out. So the reason why we can't apply reinforcement learning, which is basically just a learning algorithm based on the reward signal, is we don't have representative data, right? So we need to be able to experience how it should be somewhere else before deploying it. And the question that you asked, I think if we catch the problem in a solvable way, then we can apply machine learning, like the one that I mentioned. If we have data set, if we understand the data and build a model that is representative of the real world, I'm pretty sure we can leverage AI and machine learning for any space application. But the main problem is we don't have publicly available data sets. And here I just invite everyone else who can share data for experts to play with. That'll be awesome. Then we can come up with AI and machine learning solutions.
Thank you, Rashid. And one interesting question from Rocco, how long it takes to a company, and the question is valid also for Rashid and maybe for Red as well, how long it takes to the company from day one to build the model and the software first and become profitable then? Because we guess it takes some time. So maybe Juan or Rashid, that you have.
I've seen some. The fastest I've seen is 2 years, but then it's usually 4 to 5 years. Yeah.
Maybe Juan first, and then I can just contribute.
It's quite challenging, of course. It depends on the resources that you have, as Rashid was explaining, on the data sets that you have. The more, let's say, time-consuming thing for us, at least, is to prepare the data sets. That is very time-consuming. Then it depends on the problem that you're addressing. But I would agree with what it was already said. Less than 1 year, it would be, very challenging to get something with high accuracy.
And same, you can maybe, whenever a job package comes to me, first I ask the question, can AI and machine learning be used? Do we have enough data? And if this is the case, how long it will take to label everything else? Because let's be honest, everything else we do is supervised learning. All others, early stages, right? If you want to deploy a solution, it's supervised learning. We help machine to learn as humans. So 90%, maybe 85%, if you are very careful, you spend for data preparation. Then machine learning part comes, later stages. So the fastest that I do is 9 months, but this requires a lot of sleepless times.
So I think we should finish now. I'm sorry because we cannot address all the questions, but we have a limited time. It was really a pleasure from my side to meet you, Juan, Rashid, and Red. Thank you for your time, and thank you for your passion, and thank you for your good vibes today. See you next time.
Thank you for the opportunity, Ivan.
Meeting with you.
Yeah. Thanks for the council. Yeah, thanks everybody. Very interesting questions.
Keep in touch.
Keep in touch. Bye bye. Thank you very much.
Yeah. I'll be back.
Thank
I
you
just
very
have to. Ciao.